tomorrow while I'm gone, you're going to talk about independent and dependent events in probability. So remember, we've been working with probability, and probability is what you want out of total possible events. Now, sometimes we have more than one thing happening, and that's when we have what we call independent or dependent events. So if the outcome of one event does not influence the outcome of a second event, then that's what we call independent. So they each stand alone. So an example of that, and this is when we have more than one thing happening. If we have 12 red bells and 12 silver bells, we pick one. Here is the key. We replace it. That means that when we pick the second time, we still have 24 bells in the bucket or the jar, whatever we're picking. We pick another. What is the probability of picking a silver bell twice? So we know that we have a total of 24 outcomes. So that, of course, is our denominator. So we want the probability of a silver bell, and we want the probability of another silver bell. So we have 12 silver bells out of 24, which is where this 1/2 comes from. We put the silver bell we pick back into the jar. So there are still 12 silver bells out of 24 in the jar, which is, again, 1/2. When we have more than one event happening, we are going to multiply our fractions. So 1/2 times 1/2 is 1/4. And that is independent because at all times we have 24 bells in the bucket. Now, if the outcome of the second event depends on the first, then that is when they are dependent. Makes sense, dependent. And what happens there is that you do not put it back. So we call this without replacement. So the first one, we replaced it, so there are 24 at all time. But now we're going to pick one, and we're going to leave it out. So a jar contains 12 red and 12 silver. We pick one, we keep it, and then we pick another. So that means that when we have, so we want the probability of 2 red bells. So probability of red and the probability of red. Well, when we pick the first time, there are 24 red bells or 24 total bells out of 12 red in the bucket, which is where we get the 1/2. However, if we pick one and we keep it out, now there are only 23 bells in the bucket, and out of those, 11 are red, which does not simplify. So you can see they did top times top, bottom times bottom. 11 out of 46 is the probability. That means if we did this experiment 46 times, 11 times we should get red and then red. So we're going to do a little bit of practice with this. It says refer to the 10 buttons on the left and find the probability of each outcome when each one is replaced. So this is what we call independent. There will be 10 buttons in the bucket at all times. Now, it's very, very hard to tell based on the colors, but these are the black buttons, and these are the gray buttons. And then obviously those in the middle are white. So a white twice, so the probability of a white and then a white. Well, 3 out of 10 are white. Even if we pick a white button, we have to put it back because it says we're replacing it. So the second time we draw, there are still 3 white buttons out of 10. Top times top, bottom times bottom. That means out of 100 times doing this experiment, we would get white, white 9 times. Okay? I'm not going to do all of these examples. We're going to just do these. A gray button, so we want the probability of a gray and then a white. Again, we are replacing these. So gray is 1, 2, 3, 4, 5 out of 10. I know that that's 1/2 times. I put the gray button back, so there are still 10 in this bucket. And 3 out of 10 are white, top times top, bottom times bottom. So if we did this experiment 20 times, 3 times we would get gray and then white in order matters there. We'll try a black button twice. So yeah, we have 2 out of 10, which we know is 1/5. Even if we drew one, we put it back, so there's still 2 out of 10, 1/5. So 1 in 25. times. And that is with replacement. That is independent events. Now, if we're looking at these same 10 buttons, but now we are not replacing it, this is dependent. And remember, that means that the denominator changes. All right, so let's look and see what happens. So we're going to do these same 3, and we're going to see how it changes. So we still have probability of a white twice. Well, probability of a white on the first one, we have 3 out of 10 total. But I drew one. I took it out, I didn't put it back, so I'm just going to cover it up. Now I have 2 white buttons out of 9. And we know when we multiply fractions that we can cross-reduce. So 1 out of 15. We would get white and then white. So when we go to number 9, we're going to again start with 10. A gray and then a white. So gray, again, we have 5 out of 10, so we have 1/2. But again, we've drawn a gray, and we're not putting it back. So that means now we have 9 buttons, 3 of which are white. Well, 3 out of 9 is 1/3. So the probability of a gray and then a white without replacement is going to be 1/6. Finally, we have a black and then a black. So we have 2 out of 10, again, 1/5. But now I've drawn one. So now there is only 1 black button out of 9. So that is 1 in 45. So that is the difference between independent and dependent events. On the back, the second thing we're going to talk about today is still compound events. Sometimes we have, again, dependent or independent. And then we're going to talk some new words called exclusive and mutually, or inclusive and exclusive. So when 2 events cannot happen at the same time, they are mutually exclusive. So that means that one happens and then the other. Okay? So here's an example. And we see this with when we have the word or, right? When we have 2 things. A die is tossed. What is the probability of 5 or a 6? Well, these are exclusive because you can't get a 5 and or a 6 at the same time. You have to roll the die and then roll the die again. So, events are, and it tells you that right here, cannot land on 5 and 6 at the same time. Now, they've got it where the probability of 5 plus the probability of 6. We know that our possible outcomes on a die are these, 1 through 6, and you can get a 5 or a 6, that is 2 out of 6, which is 1/3. So you can do it with the addition, or you can just look at it and see how many they are. When 2 events can occur, they are inclusive, so they're including things. So if a die is tossed, you can get an even or a number greater than 4. Well, you can get both of those at the same time. So this is called inclusive. Now, again, they're adding and subtracting and such. If you just list out your possibilities and even, so even numbers are here, and greater than 4, the only number that doesn't have a check mark greater than 4 is the 5. So you can see that there is 1, 2, 3, 4 out of 6, which is 2/3. So you don't need to memorize this whole plus and plus minus thing. If you just look at what you have, you can count them. So we're going to decide if it's inclusive or exclusive and then find the probability. So we're going to use these theater seats. 18 best seats in the concert hall. The tickets for the seats are given away in a raffle. A seat in row A or in row C. Now these are exclusive because you can't be in row A and row C at the same time. What is the probability of being in A or C? Well, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 that we want in A or C out of 18 total seats, which is a simplification to 2/3. Okay, or 2 rows out of 3. A seat in row A or a seat number 3, well, this is going to be inclusive because you can have both of those at the same time. So now, make sure you don't double count this one. So in row A, 1, 2, 3, 4, 5, 6, or a 3, we're not going to double count this. 7, 8. Okay, 8 seats out of 18 meet that criteria. We can simplify that to 4/9. 2 or 5, you can't be in row 2 or have a seat with a 2 and a seat with a 5, so these are exclusive. And then 3, 6 out of 18 total seats is 1/3. A, B, or C. These are all, this is exclusive because you can't sit in all of these rows at the same time. So that would just be a probability of 1 because it's everything. A 1, 2, or a 6, again, these are going to be exclusive. 1, 2, 3 out of 6 total rows, so that's going to be 1/2. Now, an aisle seat or a seat in row C. So that is going to be inclusive because that could be this one, okay? And we're going to say that the aisle seats are seats labeled 1. So then we have 1, 2, 3, don't double count this, 4, 5, 6, 7, 8 seats out of 18, which again is 4/9. An odd-numbered seat or a seat in row C, those are going to be inclusive because row C has odd-numbered seats. So 6, 7, 8, 9, 10, 11, 12 out of 18 is 2/3. A seat in row C or prime. Okay, first of all, 1 is not prime, okay? Prime numbers out of 1 through 6 are going to be 2, 3, and 5. So that's going to be inclusive because row C has those things. So 6, 7, 8, 9, 10, 11, 12 out of 18 is going to be 2/3. And, okay, not in B or a seat number 2. Okay, these are again inclusive because B and 2 are the same. So 6, and then we've got 12, and then we've got B2, 13 out of 18. So those are mutually inclusive and exclusive as well as independent and dependent. So hopefully you can be successful on your practice paper tomorrow. I will see you Monday.